So hello and welcome to this first afternoon session. I know it's nap time, so I'll try to be dynamic to keep you awake. So my name is Paul-Antoine, but you can call me PA. And I'm going to tell you about some analysis work that I've been doing for a bit more than a year now. I started, I think, late July, early August last year. And so on and off, I've been trying to make some meaningful comparisons between the code generated by GCC for both the RISC-V and the AArch64 backends, with a view to improving the quality and the performance of the code generated for RISC-V. So I'm going to go through first a bit more details about the context, what sparked this work, what kind of experiments I've been doing. Then I'll give you an overview of the results, and I'll dive into the details of the analysis and a bit of the implementation. By the way, feel free to interrupt me to ask questions as and when. No need to wait for the end if you have a question. So first a bit of context. So this work has been carried out as a collaboration between two companies, BayLibre and Rivos, and it has been funded by the RISE project. So the starting point of the whole study was an observation that in a number of benchmarks, RISC-V GCC trails AArch64, and well, specifically for SPEC benchmarks. I'll go back to that later. And that begs two questions. First, why is that? Where are the key areas where improvement can be made to bridge the gap? And second, how, practically speaking, can we make the code generated by the compiler better? So it is thought that large gains can be made, and that's one of the reasons why the metric that was picked, so it was a prerequisite, let's say, in the project. That's not a decision that I made, but the target metric in this project was the dynamic instruction count. I give a few explanations about that in just a minute. And one last methodology point, the analysis would focus on the assembly code in hotspots, so the part of the code that are executed the most for a specific run. So, as I said, I'm going to explain why the metric here for this particular study is the dynamic instruction count and not something else. So first, everybody knows the pitfalls and the shortcomings of counting instructions as a proxy of performance. First, obviously, it's not directly proportional to execution time. Also, it ignores the differences in cost between different kinds of instructions. And also, and that's important for this particular study, it can be misleading to compare the instruction counts between different ISAs, so in this case between AArch64 and RISC-V. But there are a few advantages that are, first, it's vendor neutral, so it doesn't, let's say, favor any specific hardware or design. It's easy to measure with the simulator, which we did. More about that in a minute. And also because in this precise case, it's known already that there's a large performance gap between AArch64 and RISC-V. In this precise case, it can be a good first-order approximation for performance. So just a bit of terminology. Here we'll be talking mostly about dynamic instruction count, which is the number of instructions executed during a given run, not to be confused with the static, let's say, I count, which is the number of instructions that can be found in the executable file or in the binary loaded in memory. So what are the kind of experiment, the meaningful experiment that we can do in this context to carry out such analysis? So we've got two target architectures, as I said, AArch64 and RISC-V, but more precisely, we're interested in comparing the vector performance between the two ISAs. So for ARM, that means SV2, and for RISC-V, it means the V standard extension. In this case, we're targeting a vector size of 256 bits. And the reference benchmarks that we've been using are the SPEC CPU with the reference dataset, which are the largest dataset that we can get for those benchmarks. So I did several rounds of analysis, but the results I'm going to present you today are the latest ones, so from the latest 15.2 release from last month. So for reference here, you can find the exact flags that were passed at build time to GCC. And in terms of runtime environment, so we've been using mostly QEMU in user mode, plus we've been helped by a plugin developed by Rivos. I'll say a few words about the plugin later, and here, for reference, you get the exact flag that I used. So this plugin, contributed by Rivos, helps us in two ways. First, it gives us for each run the total dynamic instruction count for that run, which is, let's say, the starting point of the study to know which are the benchmarks that exhibit the largest difference between the two architectures, to know on which benchmark we need to focus. But then, as I mentioned earlier, here we're interested in hotspots, or here we're going to call them top blocks, which are segments of string-like code that can be easily analyzed. There is one tiny difficulty here with QEMU. So the way QEMU works, without going into the detail, is that it uses blocks that are easy to translate into JIT, but are not really not as easy to analyze in terms of what the compiler is doing. It doesn't map exactly to what we know from a compiler perspective, which is the control flow graph basic blocks. So what the plugin does is that it helps map the TCG, as they call it, blocks from QEMU onto the basic block that we compiler engineers know. And with that, once we got the basic blocks, we can tally the dynamic instruction count for all of them, sort them by frequency so that we get the hottest spots first, and report all the top blocks. So to give you an idea of what it looks like, here you've got two top blocks reported by the QEMU plugin, both for AArch64 and RISC-V. So you can see this example is pretty simple. In practice, it's usually more complex than that, but here you can see it's relatively small blocks, like 14 or 13 instructions. Block 0, so it just means that it's the very first block, so the hottest spots. You get the number of times this is run for each of those, and the percentage figure that you get is over the whole run. So for AArch64, for instance, you can see that this chunk of the solve function takes like 15% of the time of the whole run in terms of instruction count for AArch64, and for RISC-V it's a bit more, it's 17%. Here the analysis is pretty simple. It's you get more or less the same instruction, but if you look at the number of times each of those basic blocks is run, you can see that RISC-V runs it exactly twice as AArch64, and that's because AArch64 unrolls the loop. So this is actually the body of the loop. AArch64 unrolls the loop, so you can see I put two colors, so blue and red, to show the instructions that are from one or the other iteration. So yeah, I mean, in this case, there is not much that can be done, but it's just to show you what we can see just from looking at those top block reports. Now, before I show you an overview of the results, just a few words about this board. So this is real RISC-V hardware. As I said, most of the experiments of the measurements were done on QEMU, but for very specific tests that I've been doing, for instance, testing one patch to see if it has an actual impact, not only in terms of eye count, but also in terms of real timing. I viewed this board in those cases. So here for reference, I'm giving you the specs. So what is important here is that it's the vector length that I mentioned earlier, 254 bits, and also it complies with the RISC-V extension standard 1.0, which is the one that's been frozen and ratified. So there were earlier designs, but they were complying with an earlier version of the standard. So this one is the one that matters. Right. At last, we get to the result. So I've got two views for those results. This is the first view. This is the absolute number of instructions for all the benchmarks. So AArch is in AArch64 is in blue here, and RISC-V in red. So the order of magnitude of the number of instructions is around 1 trillion for each benchmark. So that's quite big. So the reason is because we fed the benchmark with the largest data sets that we had, the ref. And we can see that over those 20 benchmarks that I picked, so there is a mix of C, C++, Fortran, integer, but also floating point computations, and some of them are vectorizable, some other are not. So it's supposed to represent a bit of all kinds of computations and source code that can be run. So to see the difference of dynamic instruction count between the two architectures, so I've got this view that is a bit clearer. So you can see that the difference in I count ranges from, let's say, 50% to minus 5%, I think. So there are a few benchmarks where RISC-V is actually better. So those are the last two here, 548 and 505. But for the most part, for 18 out of 20, AArch64 is actually better in terms of I count. In some cases, like X264 or Cactus or Photonic, it's quite significantly better. So this is just an overview. Now I'm going to go into the details of, not all of them, but a selection of those benchmarks that I spent time on to try and understand why we can see those quite large differences, and if there are some ways to reduce this gap. So first, a few words about Cactus BSSN. So this one has a very specific kind of basic blocks. Well, they're huge. The basic blocks are huge. So you can see here it's the order of magnitude is like 3,000 or even 6,000 for RISC-V. So if you really want to go down this basic block and read each instruction, is going to be difficult. So I had to do some frequency analysis to see exactly which instructions would come more often. And what I found is that, so here you get the third column that we don't have in the first example. Here is showing you the difference in dynamic instruction count if we take AArch64 as a reference. So here we've got more than twice the number of instructions for RISC-V compared to AArch64. So that's really a huge difference. And also since this top block account for more than a third of the whole run, well, that's definitely something we should look at. So I found two interesting issues. There are more than that that have been analyzed here, including by Vinit. But here I'm going just to show you one specific point that I looked at. So first, what I call the redundant add I. So you've got this exact sequence of code, so two subsequent add I, both writing into the same register, in this case A0. And obviously, since the result of the first is not reused, well, the first add I is basically functionally dead code. So this should be removed, but this pattern happened really many times. And the second one that actually happens to be the same issue is what I call the missed load offset. So you start with an add I that's just going to increment some address in a register, and then you've got a load that's going to read from the address pointed to by, in this case, T1. But here we've got an immediate offset, 0, that is unused, and we could just fold the add I into the load and just say, okay, load T1 plus 1 here, and then we would get rid of the add I in this case. So I did some work, but actually what I found was that in the Alpha scheduler there is a feature that allows to replace some operands between instructions, and that was this operation of replacement that would leave the first add I without removing it. But actually, it turned out to be just a side effect. Actually, the real issue was earlier in the pipeline, so it got investigated by Jeff. Shreya came up with a patch, and I think yes. So that's what we should do. And yes, so we are basically waiting for the patch that Shreya is working on. But according to what Jeff said, that looks promising. So second benchmark I can tell you about. This is photonic 3D. So this one has much smaller basic blocks. So this one is the top block for both AArch64 and RISC-V. So 42 instructions on one side, 63, so that's much more manageable, and still quite high percentage, like 22 and 24%. But still, we've got like 50% more instruction on RISC-V, so that's definitely something to investigate. And it turns out that this one has nothing to do with the comparator itself. It's really an ASL limitation. So this code is not RISC-V. This is AArch64. So this is a load. But if you look at how it's done, so well, it's loading into a vector register. So Z30. The base address is in X3, and you've got the offset in X0. But here, what we are doing is that we are shifting the offset left by 2. So this has to do, this is like a typical operation that you have when you're looping over array values, and the shift is just here to adjust to the type of the array. So in this is particularly important in this basic block, which is basically just a sequence of loads and stores into arrays. And so every time you have to do that, well, for AArch64 it's easy, it's just one instruction, but for RISC-V you have to add an extra instruction just to adjust the offset, so doing the equivalent of the LSL, which is just regular add I. There is no, in this case, it's really like a limitation of the ISA.
Is X0, where does X0 come from? Is it an induction variable, or is it just
Yeah, X0, yes.
If it's an induction variable, wouldn't you just have it to add, add by 4 each time instead of 4? Yeah.
Yeah, well, in this case, what happened if I don't have the source code of the loop exactly, but in this case, if I remember correctly, what happened is that you've got different arrays with different sizes, and you've got one induction variable, and you have to use it for different sizes. So every time you have to adjust.
Then why not have multiple induction variables? But yeah.
Yeah. Well, in this case, I mean, if in simple case, yeah, you just add exactly the size, but in this case, yeah, unfortunately, the only way is to shift or to add. So yeah, I mean, in this case, there's not much that can be done at our level, at least. But that's definitely something in terms of the ISA. That's definitely something for which, especially for vector computation, where AArch64 is superior to RISC-V. There is still one last thing that I want to mention on this benchmark before moving to the next one. this is the length multiplier. So we've got this Helmholtz max that is set at compile time, and which defaults to 1. But if we set this Helmholtz to higher values like 2, 4, or 8, it's possible to group registers and to have one instruction, one operation applying to, instead of just one, like 2 or 4 or 8 registers, which is like semantically kind of similar to loop unrolling, but this is baked into the ISA. So, well, if we look just at the dynamic instruction count, you can see that there's a tremendous difference between Helmholtz max set to 1, which is the default, or to dynamic, which allows it to vary depending on the computation. Actually, it even gets, for this basic block, it even gets better than AArch64. But that's one of the many cases where the dynamic instruction count is not giving us really useful information, because in practice, if you try that on an actual design, I mean, depending on the microarchitecture, of course, but you can get actually worse performance. So that's all I had for the photonic benchmark.
Is that a new thing, LMAX being limited to 1? Is that a new?
Well, new since 14.
Oh,
So that's still up to discussion what to choose. But now it's 1.
okay.
Well, it can be 1 or 2, but definitely not 4.
Right.
Yeah, all right.
Yeah.
But the unused is 2 by default.
Yeah, that is
Okay, so next benchmark. So here, ROMs. What do we have? So this one is interesting because there is a kind of mismatch between the top blocks. So if we look first at the RISC-V size, so the very first block, it's relatively short, 38 instructions. It accounts for 6% of the run, so it's not as huge as before, but it's still significant. And this is the EXP, so the exponentiation function. And you can see that if we look, so I had to go through the AArch64 assembly as well to find the matching blocks. Actually, I couldn't find exactly matching blocks. The closest I could find was those two, so block 1 and block 4, and they're actually calling 2 different variants of the same function, and it ended up being much more efficient than RISC-V calling always the underscore exp. So I had a look at that. And actually, it's not specific to exp. That can be reproduced for basically all math functions. I mean, not all, but many math functions in libm. So, but for the sake of the example, let's just focus on the exp function. So on AArch64, it's 1.64% of the run, of the whole run. On RISC-V, it's 6.21%. So that's, I mean, it's not as huge as 30%, but it's still like a significant difference. So underscore exp, it's the generic scalar implementation of the exp function that you can find in libm, distributed and used everywhere. But there is another version of this. And this is going to remind us of what we talked about this morning, what Alfie talked about this morning. So in libmvec, you can find some target-specific versions of exp, including vectorized version. So that's what the mangled name that we saw earlier here is actually designated. So for AArch64, 80% of the calls are actually turned into this mangled version, which happens to be vectorized and so much more efficient. For RISC-V, that just doesn't happen. So clearly, in terms of instruction count, it's plus 32%. So that's a clear difference. So I had a look exactly at what was going on there, and if there was some work toward that direction, and the answer is yes. But it's difficult because there are three aspects to it. So yeah, as I stated in the title of the slides, AVI, compiler, and library, and all three have to agree. So on the ELF PS ABI side, there is a PR that's been open to discuss the name mangling. It's been going on for, I don't know, maybe a year now, but hopefully it should converge at some point. And once the ABI is set, it's possible for GCC and glibc to agree and to call the function with the right name. In terms of what has to be done in GCC, it's actually handled by the SIMD clone pass that has to be enabled. So there is a target hook for that. It's compute vex size and SIMD len. And on glibc side, well, obviously, the actual implementation has to be done. But I think, at least, well, for the PS ABI, there is a PR that's open, that's sure. For glibc, I think that there was some work that has been done and submitted, but as far as I know, nothing has been merged. And yeah, obviously, the relevant work has to be done on GCC.
So just to add a little bit, right? So for EXP, I don't remember the specific sort of vector build, but ZFA is a new extension. I don't think your builds are using that. So with ZFA, the EXP in particular has this round to int and convert to int, two macros, which are not accurate, but they need to match each other. And I think AArch64 has a single instruction for both of them. Otherwise, we resort to this fallback math in EXP code.
Yeah.
I'm pretty sure I saw on the glibc mailing list somebody posted a patch for that. I think I even tried it 2 years ago. So that should be a low-hanging fruit, really. So it just needs to be merged. Of course, the problem becomes then, with multi-living, how do you have two variants of EXP and all that? But I think that's a separate problem on the side anyways. But I think ZFA definitely should help, at least for the baseline.
Okay. Yeah, I didn't try. I did some experiments with that, but ZFA, no, I didn't try for sure. So yeah, it might be a way, yes. Okay. So, okay. So, yeah.
Because mobs is a specific to do memset.
Yeah. Yeah, exactly. I've got the exact code showing what's going on there. But I mean, it's kind of a pathological example, but in this case, it's interesting. I mean, you can see here what's going on. So, on SPEC, for some benchmarks that are short, they have several workloads. So here, it's only one workload that has those results. If you try to replicate that with others, the difference between AArch64 and RISC-V is not going to be as significant. So I really took like the pathological case. And you've got the command line for reference. But here, yeah, you can see. So if you look at calls to memset, on RISC-V, it's the top spot. It takes like 20% of the time. And for AArch64, it's like 70, so it's basically at the bottom, and it takes 0.13%. But yes, as you said, it's not the same function, because on AArch64, it's using the MOPS optimized version. So if we take that piece of code from GCC, so that's one of the examples where the memset comes from. So I counted the exact number of instructions, so dynamic instructions, that are actually run for this call to memset. So for AArch64, it's just 5 instructions, and for RISC-V, it's 46. So imagine that being run many times. So there is something to say. So there is the MOPS implementation in libc, which is one thing, and also the fact that GCC knows how to expand, or at least is supposed to know how to expand efficiently memset without even having to issue a call to libc. So actually the question when I saw that was, why is memset not expanded by GCC for RISC-V at all, at least in this example? Because RISC-V does support vectorized memset, right? There is code in the backend. If you look in the RISC-V string.cc, you can see there is a function just for that, expand vex set mem. But in some cases, it's too restrictive. And I think where I haven't looked exactly what was going on, but I think if we check use vector string of P, that's where the decision is made whether or not to expand with vector instructions. So I think sometime last year, Craig Blackmore came up with the patch to help with that, as it says, make vectorized memset handle more cases. But I tried that, so it was supposed to make it work with smaller vector length and also for smaller LML values. But in this precise case, I didn't see a significant difference. So it might still be too restrictive. So yes, in the end, what happened is that GCC tries many different things, but this is what's supposed to be the most efficient, at least for RISC-V. But when you go through all the possibilities in the list and nothing works, it just falls back to set storage via libcall, and it ends up in a call to memset from GCC.
Well, you are compiling with a vectorized multiplet.
So, very good point. Yeah, so I don't have it in this. I thought I had that. Yeah, it's here actually. The answer to the question is yeah. So yeah, the thing is, well, depending what kind of glibc you have, how it was built with or without vector support or even support to other extensions that can help. That makes a difference, but I'll say a word about that in a second, but I just wanted to show you, especially since Andrew mentioned it. So this is how the MOPS optimized memset for AArch64 is done. So, well, this morning, Alfie was talking about function multiversioning and ifunc. Well, you've got an example here. So it takes two things, a handwritten implementation, you've got it here. So yeah, it's as simple as it gets. Those three instructions that are doing exactly that really tailored for that use. So yeah, you won't beat that. But you also need what they call a resolver function. Sorry. So it's basically a list of functions that functionally do the same things. Here it will be a list of different implementations of memset. And depending on the features of the CPU that are tested dynamically, you will get one or another of the outcomes. And if everything fails, you get the generic version. But actually, yes, I have explanation here. So if you have glibc built, which is by default with optimization, but without vector extension, that's what you get. But yes, if you build a glibc with the vector extension for RISC-V, yeah, I did the test. I don't have the figures here, but yes, it decreases from 20%. It goes down to maybe 7%, something like that. So it's still not as good as AArch64, but yeah, still much better. But anyway, the point here is that what's missing, the piece that's missing in the puzzle is the implementation of memset as an ifunc for RISC-V in glibc. So we need two things, the handwritten assembly and the resolver function that I just showed you on the previous slide. Just a few words about how the resolution works. So this resolver function is called actually only once, the very first time that you encounter a memset at runtime. This function is called. It tries all the possibilities, so it checks dynamically the features that are supported by the CPU, and based on that, it calls the most optimized function, let's say, for that variety of CPU. And well, obviously, to avoid having to do that anymore for the rest of the run, it updates the procedural leakage table, and then for the next calls to memset, it will jump straight to the right optimized version. So actually, I found that there was a patch that was submitted by Jeff. I think it was actually an older patch that was written by someone else, but Jeff picked it up and he submitted it to the glibc mailing list. probably late last year, I think. You can find it. It's called Enable Vectorized Memset via iFunk. But I think you reviewed it, actually, Andrew.
There's new one as well.
Yeah. Yeah. So, but anyway, this, there is this patch that was submitted, but I checked again, I think yesterday or the day before, it hasn't landed yet. But basically what it does, so here I gave you the example of the resolve function that was in this patch. So, well, since in this case, the only variant that is proposed is memset vector, there's just one check that is done here, RISC-V web probe 1, just checking that the V extension is supported. And that in this case, it returned the vector memset. And if there is no vector extension, it just returned the generic memset. So I think it's just a matter of, I don't know if there's anything blocking, but that would probably be enough to make things much better for memset. Okay. Now, something a bit different. Now let's talk about floating point vector operations. So on the ROM's benchmarks, we've got this sequence of code. It's not the top block, actually. It's a bit further down, but it still caught my attention. So we've got those two instructions. So the first, vector floating point move. So it's actually a broadcast from a floating point scalar register to a vector register, and then using this value for a vector FMA. And actually, when you look at the spec, you can see that there are two flavors of the VFM add, but also pretty much all other vector floating point operations. So one that takes only vector operands, and one that also takes scalar register. So they're called VV and VF, respectively. So I thought, why not combine the two, the VFMB and the VFM add, into just one VFM add, but not VF, the one that actually accepts the scalar register. Well, that's definitely doable. So if we look at this sample piece of code, so the important part, the important pass in this example, it's either combine or late combine, depending on the case. But anyway, the result is what you see here. So this is the dump. You have to enable the details for the combined dump, but that's what you get there. So you get the vec duplicate here to do the broadcast, and you want to combine that into, so here this is the R148, and you want to combine it to use it directly into this instruction. But because, for a simple reason, in the machine description of RISC-V, there was no pattern matching this, so well, it's not that difficult. It's just a set plus mult with a vec duplicate. So I created a set of new patterns. Well, first I created a pattern for VFM add, and then I did the same for the others. But it's basically what you see on the screen here. So it's just plus minus with the mult, vec duplicate, and then you just get the to VEL. Here it's a placeholder for the Yeah. So just one element, yes, one scalar element of the right mode, and yes, and then well, there's some RISC-V specific stuff. You need to call emit VLmax in with the right code, but yeah, that's in RISC-V, in the RISC-V world, is quite classic. And then after that, you get your combination just like that. And so you can remove one instruction, one VFMB, but you can also free one register because you don't have to go through to use one extra vector register. And so assuming that this value is not going to be reused later, well, you just freed one register on top of that.
You might also want to add that in your example, the F is like loop invariant, so you would rather hoist it out and save it in a vector register to like not have scalar to vector crossing in
Yeah.
each iteration.
Yeah. In this case, yes, that works as well. Yeah, indeed. Yes, so I did that for all those floating point instructions. Well, it's a bunch of them, but especially so you've got the classic add sub, multiply divide, both single width and widening variants. Well, honestly, some variants, especially the widening ones, are rarely used, so I don't expect to get any performance out of that. But anyway, for the sake of completeness, I did all of them. So yeah, those 22 instructions are now supported in the combined path. And what do I want to say? Yes, so it was sequence of patch series, so all of them, each of them introduced the new patterns. You get the new test. Also, the cost model had to be adjusted, but to be fair, I didn't have to do much for that. Panly did much of the job for that. So now the question is, do we get any performance? I mean, do we actually get some reduction in terms of eye count? So I look at ROMs, at the results of ROMs. So we get at the basic block level, so the block I showed earlier is -9%, and for the whole run, for the whole benchmark, it's 0.28%. So yeah, it's definitely not a huge win, but yeah, at least we get some measurable results. So I ran that on the BPI, on the Banana Pi board that I showed you earlier. On the Banana Pi board, it doesn't make a difference. I think maybe the little you would have won is actually negligible compared to the cost of the actual arithmetic vector floating point operation, which is on this unit not very powerful. So anyway, this is implemented. It has maybe I can say something about the cost model adjustment. So the cost of moving data from different register files, so in this case from the floating point registers to a vector register, can vary depending on the microarchitecture. So there is a tunable to adjust that, and obviously, if it's too costly, you don't want to have that optimization. Right, I think that's all I had to say for the vector scalar and the run thing. Oh, actually, no. Actually, we still have some vector scalar interesting example. So here, okay, that looks very, very similar to what I showed you earlier. You've got the VFMV and then the VFM-ACK, and this vector register that just got broadcast, it reused here. So I thought that the patches that I worked on just before were handling that. Well, actually, this example is slightly different. In this case, the reason why we don't get VF variant is because actually the RTL looks like this. So you've got a vec duplicate, but the vec duplicate here is actually not directly duplicating a register, but a memory operand. So actually, that's exactly what you see here. So first you have to load into a scalar register in this case, and then you can do the vec duplicate. But in this case, it's done in 2 steps. And the question is, can't we not do that in just 1 step? Or say differently, like broadcast from memory? Well, there is an interesting instruction in the RISC-V extension, which is called VLSC. And what it does is that it's actually a strided load. But if you use the special case where the stride is 0, well, you're basically reading from one memory register and duplicating this value into all the elements of a vector register, right? So here we are faced with those 2 options, the vector scalar that I discussed before, or the 0 stride load that looks like this, so VLSC, and then the zero strain. So I made some experiments. I came up with a very, very quick patch, basically just saying, okay, in the case where we have a floating point mode and we are reading from memory, so not a constant, but really a memory operand. In this case, instead of doing a regular broadcast, so the VFMV I showed you earlier, in this case, we're going to do a strided broadcast, so which is effectively a VLSI. So I looked at the dynamic instruction count, and I was very happy to see that on D-Wave I got -4%, -3% on Imagic. Well, Cactus, it was a bit weird, plus 0.43% that I haven't investigated, but at least that looked promising. And then I ran that on the BPI board, and that's what I get, terrible performance, terrible. From +5 to +11, so I thought that I made a mistake, you know, so I rerun everything, I checked, no. That's actually what we get. So that, I mean, if that has to go anywhere, it will need some kind of microarchitecture tuning or something like that, because yeah, obviously, at least on the BPI, it's just pessimizing rather than anything else. So yeah, actually, I just posted the patch earlier this week, so that's really a work in progress. Okay, so well, I think it's time to conclude. So. Well, breaking news, performance optimization is hard, but performance measurement is hard as well in the first place, so that doesn't help. And when you have a deceptive metric like the dynamic instruction count that not always, but very often gets contradicted by actual hardware performance, that doesn't help. But at least, yes, I showed you a number of areas where I could see that there was some improvement to be made. So I think it validates the initial assumption or prerequisite, let's say, that it's a useful tool, but don't ever outfit to that metric. I think that would be the takeaway from that study. So in terms of implementation, I told you about the vector scale patches. The VLSI, it's ongoing. So yeah, to be continued. In terms of expected improvements that I'm not involved with directly, but I'm checking from time to time, and there is some progress being done. So yeah, SIMD math functions to have more efficient EXP and function like that. Memset, and actually not only memset, but all the memset family functions. And I can suggest some future directions because now the project is coming to an end. But I mean, if I had to work again something similar to continue, here is what I would do. I'd be curious to see the difference that Shreya's patch makes on Cactus because that's was the most obvious limiting factor that we could see, but I'm pretty sure that once this is fixed, it will maybe reveal some other issues. Because given the huge gap between AArch64 and RISC-V on this particular bench, there has to be other issues. Also, yes, there are still like a bunch of benchmarks that I haven't analyzed because obviously, in priority, I started with the one that exhibited the largest differences in some instruction count, but other benchmarks might be of interest. So you've got like a 541, Lila, NAMD, that they are around like 10% different between the two, so there are probably still things to look at. And also something that I almost haven't done. Maybe I checked one or two things just out of curiosity, but doing like the same kind of study, comprehensive study, instead of comparing GCC RISC-V with GCC AArch64, why not compare also RISC-V with LLVM? There is an interesting project by Igalia. I forgot to put the link. Yeah, I tried to add it before uploading the slides. But they do a great job at having, like, I think every night, so they run the SPEC benchmarks. So initially it was just LLVM RISC-V, but now they also do GCC RISC-V, so I didn't have time to exactly look at that, but I think that's great, and that's probably going to be helpful, not only for GCC to catch up with GCC on the benchmark where there is a gap, but also over time to see the evolution of GCC performance on those benchmarks. And that's it. That's about it. So thank you.
So, this is really interesting because we've been doing exactly the same stuff for other people. We've got very, very cynical about dynamic instruction count as being almost useless. I did do a little graph at, I just used MVec because it was small, and it's not a good choice because it doesn't really vectorize terribly well, where I did the plot of BPF speed up versus instruction count speed up. And it's sort of, beyond the fact it sort of points in the right direction, it's useless. Because there's only a few things where vector makes a big change. And when you do, the prediction from IDC can be way off. You saw, I think, one where it was 5% better instead of 5% worse.
Yeah.
We saw 50%.
Oh.
And Palmer Dabell gave an example of last year, a RISC-V BOF, where if you look at the H.264 benchmark, IDC looks fantastic with vector on there. And you turn on the vector on any real chip, including the ones that he was working on, and instead of doubling the speed halves. We've seen with some of our customer places where number of in ARM there are instructions basically for doing RGB bytes all in one go. And actually the hardware implementation has so many interlocks that we found with customers that having 4 instructions, which is what RDB is good, actually runs faster. Because actually at hardware level, it's easier to get the hardware parallelism. You're counting all the VZVL instructions on many high-end architectures. Those cost nothing because they're running parallel.
Yeah, true. Yeah.
So you could almost say my metric should exclude those because they're not going to cost you anything. So we've given up on doing any optimization. We just say we won't do any optimization until you can either give us a cycle accurate model or a real chip, because anything we do, you'll throw away and we'll start with everything.
Yeah.
So the point is, when we started like 3-4 years ago,
Oh yeah, 3 or 4
there
years
was
ago.
nothing, right?
No, I agree.
So
3 or 4
it
years
is
ago.
a good thing to start off, and now agreed, it's showing its age, it's not relevant anymore.
Yeah, but the one thing that comes out, 2 things. One is, you're right, focus on memset and memcopy, because they dominate. Okay, get those off. But secondly, the microarchitecture for the vector is absolutely critical. That matters more. I'm not sure we've got all the right books in all the right places, because you can have vector copies that are massively parallel and just take a single cycle or whatever, and you can have vector copies where your L is big and your vector's big, and it takes dozens and dozens of cycles. And it's the same instruction, and you've got to know that in microarchitecture. So, a number of times I said, do your microarchitecture before you even try. There's no point in optimizing generically because it won't apply to your chip.
They're in a tough spot. They had a contract to do certain work. They are doing it.
I
know because I helped write it.
Yes, and I sympathize because I haven't.
And the person giving the contract is also realizing that the contract is, is no longer sensible. What do you do?
Yeah. So it was a less than ideal situation. They're making the best of it.
Yeah, so I don't want to be, you've done a lot of good and useful work, but I was just saying that basically the time has passed for it.
Yes, I would totally agree.
Yeah.
And if we were to do that today, we would specify those that measurement part of the deliverable in a very different way.
Yeah. I did notice you've got quite a lot of actually scalar improvements you've done, which is great. But
Yeah. That's probably the best I was able to achieve, yes, with that metric. All right, thank you.